Have you ever really stopped to think about what's happening on a molecular level when you do, well, anything? Cooking, cleaning, just breathing? It turns out the crazy complexity of our world is actually run by just a handful of core chemical reactions. And the wild part? They almost all happen in the one substance we absolutely cannot live without: water. Yep, that's right. This quote pretty much nails it. Water is the universal stage for chemistry. It's the solvent for life itself. So if we're going to understand the reactions that run our world, we've got to start by looking at what happens when stuff dissolves in it. So to really get what's going on, let's meet the key players inside that single drop of water. See, not everything dissolves in the same way. A huge clue is whether or not the solution can conduct electricity, and that all boils down to whether they create charged particles we call ions. Okay, first up, you've got your non-electrolytes. Just think about sugar dissolving in your coffee. The sugar molecules spread out, for sure, but they don't actually break apart into ions. So since there are no free-floating charges to carry a current, that solution can't conduct electricity. Simple, right? No ions, no spark. Then you've got the weak electrolytes. A perfect example is acetic acid. That's the stuff that gives vinegar its sour kick. When it dissolves, some of its molecules split into ions, but most of them just hang out totally intact. It's this constant back and forth. Because there are just a few ions floating around, a little bit of electricity can get through, but not much. And finally, we've got the heavy hitters, the strong electrolytes. Table salt, sodium chloride, is the classic case. The moment it hits water, it completely breaks apart. I mean, every single unit shatters into positive sodium ions and negative chloride ions. With all those charges zipping around, the solution becomes an amazing conductor of electricity. Lots of ions, lots of current. All right, so now that we know our actors, the electrolytes, let's see what they can do on stage. We're going to look at three types of reactions, and you can think of them like three essential tools in a chemist's toolkit. First on the list, the precipitation reaction. Okay, this can seriously look like a magic trick. You take two liquids that are perfectly clear, you mix them together, and poof, suddenly this cloud of solid stuff just appears out of thin air. So what in the world is going on here? Well, it's not magic, it's chemistry. That solid has a name. It's called a precipitant. Basically, what's happening is the ions from the two different solutions are all mixed up, and they start swapping partners. If one of those new partnerships forms a compound that doesn't dissolve in water, what we call an insoluble compound, it just instantly crashes out of the solution as a solid. So how do chemists know this is going to happen? Well, they use solubility rules, which are basically a cheat sheet for these ion partnerships. For instance, as you can see here, compounds with nitrate in them almost always stay dissolved. But carbonates, they often find a partner they like and crash out of the solution to form that solid precipitate. Now, to really focus on what's actually changing, chemists have this great tool called the net ionic equation. It's a pretty simple four-step process that just filters out all the noise. You start with the whole equation, then you find and cancel out the spectator ions. Those are the ones that are just kind of hanging out, watching from the sidelines. What you're left with is the net equation, and it shows you only the key players that are making that solid. Okay, on to our second tool. This one describes some of the most common reactions you run into every single day: acids and bases. And at its core, this isn't some super complicated thing. It's more like a beautifully simple exchange. You can think of it as a little chemical dance. I mean, we all know their basic properties, right? Acids, like what you find in lemons, taste sour. Bases, like in soap, feel slippery to the touch. They're total chemical opposites. But when they meet and neutralize each other, what is actually going on at the molecular level? This is where it gets so elegant and simple. The Bronsted definition just cuts right to the chase. An acid is a proton donor, and a base is a proton acceptor. That's it. That's the entire dance. One molecule hands off a proton, and the other one catches it. And the result of this dance? Well, it's just beautiful. When a strong acid donates its proton and a strong base offers up a hydroxide ion, they combine to form water. The very essence of neutralization is just making H2O. So simple. And for our third and final tool, this one is everywhere. It governs everything from rust and fire to the very way our bodies get energy from the food we eat. These are oxidation-reduction reactions, or redox for short. And if acid-base reactions are a dance, well, redox reactions are more like a high-stakes electron heist. The key idea here is that redox reactions are all about the transfer of electrons. One substance loses electrons, and another one gains them. And that one simple process powers everything from the energy you get from burning fuel to the cleaning power of bleach. So, how do you keep track of which is which? It can get confusing. Luckily, there's a fantastic little mnemonic: oil rig. Just remember that. Oxidation is loss of electrons. Reduction is gain of electrons. If a substance loses electrons, it's oxidized. If it gains them, it's reduced. It's as simple as that. To keep track of this electron movement, chemists use a kind of bookkeeping system called oxidation numbers. Just think of it like assigning a hypothetical charge to every atom to see who's winning the electron tug of war. If an atom's oxidation number goes up in a reaction, it's been oxidized. If its number goes down, it's been reduced. Let's look at a really simple reaction here. Solid zinc metal starts with an oxidation number of 0. The copper ion is +2. After the reaction, you can see the zinc has lost 2 electrons and is now a +2 ion. Its oxidation number went up, so it was oxidized. And the copper ion? It gained those 2 electrons to become solid copper metal. Its oxidation number went down, so it was reduced. A perfect electron heist. So there you have it. 3 fundamental patterns that describe the huge majority of reactions happening in water, all around us and inside of us. Let's just do a quick recap of the toolkit we've put together. So, in precipitation reactions, we're exchanging ions to make an insoluble solid, kind of like the hard water scale in your kettle. In acid-base reactions, we're exchanging protons to neutralize opposites, just like an antacid soothes your stomach. And in redox reactions, we're exchanging electrons, driving everyday processes like the rusting of a nail. It's really kind of amazing when you think about it. The exchange of ions, the exchange of protons, and the exchange of electrons. These 3 simple patterns are the fundamental rules for a game that builds everything, from rocks and minerals all the way to the intricate biological machines that keep you alive. So the next time you see something dissolve, or fizz, or rust, you'll know exactly which game is being played.